improve the product. On that side. That's right.
I don't think we gave you what to do. Great. So, first of all, thank you very much for the wonderful introduction. It's awesome to be here, looking at all the people who are so fascinated and interested by PyCon. It's a great thing that, first thing that I usually wear glasses, but when I was in Karachi, and I couldn't find my glasses, so I didn't want to get yelled by my wife, so I just said, it's mic. So I can't see you guys sleeping where you are at this tonight. But yeah, that's how we stay. I just take it, so we take that out here to also that. Okay, so as I said, I'm Fahad, and we work at Motive. So my part essentially is a marketing game of what we do. But we are not here for marketing or selling anything. What my goal is to tell you that it's a big operation, very complex. How complex is it? It's my part. And how did we solve that complexity? And where this problem seamless for my team just standing there. And I'll put that in plan to develop this. So how did Numan's team work from my point of view? So to start with, as I said, here is the overview. I'll go over the company, what we do, then I give it over to Numan, who will talk about MLOps, what are the best practices, like what is awesome in there. So what is Motive? Motive is a US-based company. We have been around for 10 years. And we essentially make life easy for fleets which have a lot of vehicles. So we do driver safety products, and we go deep into that. We also do fleet management. So whenever the vehicle is, whenever we get there, and those kind of things. We do also equipment monitoring. For different type of equipment that different companies own. And now we spend management, we have a car that we can use, and we can buy stuff today, and we profit out of it. So our main, what is our main impact? The company in the last 10 years has developed all this bunch of software, and the impact is here. Our companies that buy our product before that, because of our product, they have 50%, there's more than 50% saving in their accidents. And accident in the US is very expensive. Right? There are regulation, there's lawyers fees, and so on and so forth. So even saving one accident saves a company about $1 million. So having that price is really amazing. There is more productivity, there's profitability in companies, in our companies because of using the product. There are more than 350 dash cams that are installed in different devices. There are 350,000 devices that are installed in devices in use. So that would mean that of that 150 are AI dash cams. So there's regular dash cam, which is bigger video and upload it, and then we have improved that technology for GPU in there, so it can improve compute on the edge, so that we can generate those events and give alerts and make safety products for the users by the data. These are some of the big names that we have. We have a long list, but these are the names which are more common with people, a lot of people like FedEx, University. As a team, we are about 3,500 people across the globe in 6 different countries. 500 engineering team, out of that 200 are in Pakistan. Overall, our footprint in Pakistan is about 2,000 people. The AI R&D team that I'm part of has 45 plus people, 80 PhDs, and education team in Pakistan is around here. So that is small introduction of what we do as a company. What we do, AI team does is strategy. And what we do is we have an AI dash cam installed in different devices. The customers who buy the AI dash cam install a dash cam. Is a camera installed on the windshield of their vehicle. And right on the edge, we have processing power that would allow us to process the images and generate events out of it. So if a driver is driving in a way which is unsafe, for example, the driver has his eyes closed and is drowsy, or is driving too close to a vehicle in front of him, then immediately at that time, we can alert the driver that this behavior may cause an accident. What's more, we collect that evidence and provide it to the fleet managers and the managers of those fleets so that they can coach their drivers and being better drivers. So that 57% reduction is just when the driver is not having an accident, but because we are telling them that, hey, don't drive like this, it automatically improves the performance of these companies. And that information is then used by different companies such as insurance companies, who then provide different type of incentives to good drivers so that we overall improve the driving experience on the roads. And to make this work, we have a truckload of different features, different events, different kind of things that a driver can do wrong. You capture those and you upload those videos, and you play those alerts, and to make the road more safe. Because of which, as mentioned earlier, we have 57% less accidents. Because of those lesser accidents, the overall the cost of those accidents has gone down and 21% reduction in services. So while we are building this product, there's one thing which really differentiates us from other companies. And again, marketing remains awesome, but there is one thing that really links it with what Numan is about to say. We are very good at it. We are at 86% position, and our closest competition is at 30%. These are numbers coming from Virginia Tech Transport Institute, comparative study, where they took our devices from our closest competitors, and they compare across the board for different type of features. So, for the people in that, may not be able to see, but across this red line, the numbers are stark rate of 86, 32, 92, 88, 95, 38. So, yeah, very, very good at working. And because you're not on bias, and that's not the point in your way. How did we get there? How did we make this awesome product? That is the question that you would like to ask. So, how do we create this magic? If you look at our publications and papers that we publish, what it is there? There is a video, there's a perception engine. It identifies the bounding boxes for a single frame. There's a sensitive engine model that collects the data and puts it in, and then there is a temporal modeling part of it. But realistically, this is our main market. That no model survives the market with real data. And one of the founding characters of the company that they have, that actually quite that it is great. You can have those models are available, you can download them, you can use them in different ways. But when you really send them out into the fleet on the ground, that's simple that. So our competitors are awesome, but they're much more better because we do more than that. And what we do is we take those events, those data streams that are coming in, and then improve our model consistently, continuously over a long time. So the thing that we released in 2021 is still working on. Because there's one customer who is a $1 billion ARR and something is not working. So someone from the team will go in there and say, why is it not working? So unlike other software development systems, when you make a system and it runs or it doesn't run fast or it is your own, machine learning systems are inherently different. You train a model, which is based on the data that you have already. And based on that information, you would get some really good results, but then you will see different things. For example, the first may look like at a traffic which is about to tip over, but it is a reflection of a cell phone that is on the dial. So now I want to collect data from 100,000 trucks and I pull that data back. Chances of this happening is very rare. Even if it is 3% of the data. I'll train the model, I'll get 97% accuracy of this reading. But when our model sees this and says that, hey, there's a vehicle about 2 meters in front of me and I'm about to hit it, it would generate one event every time our state machine goes back to zero. So we would have 150 events coming from this table. So a 3% precision loss and a single frame level ends up causing 30% of failures on the field. Because when it goes out, the real world, and it acts with that model different. Here there is smudge. You can't see the red balls, but there's a part which really looks like an SUV. Can't even take it all. We went to maximum, the event will change. Right? Then we have this last element, which is really interesting, can't see it very well because of the distance, but the person is very clean and neat and he polished the hood so well that everything in reflection of the vehicle on the hood. So the model saying that's the vehicle, what they didn't go. The models guys would say that, hey, let's get more data and train it. But that is a continuous improvement. So we train a model which is awesome. And then we train another model which is awesome. And then another model. But this thing keeps on going. It never ends. So, how do we solve this problem? The first solution that mostly is taught in books and papers and other ML documents, getting more data. So right now we have 1 billion miles of road covered every month. The devices that are in vehicles, they cover 1 billion miles in a month. There are 2 billion images selected. 20 million minutes of annotated video. So 1 billion miles, but we upload everything, 20 million of minutes of annotated videos uploaded, and the availability is 200 videos. So 1/10 of that is actually covered. So from that perspective, we collected a lot of data. Then we also built up a really amazing tool for annotating our videos. So we want just, it's not just that whether it is a true or false event, but what type of work condition was there? What type of time was there? Was it a city street or highway? All those things. That were important for us. We all collected that. But we still got into a problem where collecting all this data and going over it and improving it was costing us so much. Costing it becomes time. So when we develop a model, initially they are around 70 to 80% precise. We send it out to a smaller set of teams and we run it for 3 months. In 3 months, we collect more data, more of these edge cases, resolve them, and then go back, send those reports out to peaks, still getting more errors. At one point, we reached an acceptable limit where the customers won't accept and won't throw our devices away. And then we send it to everyone else, and then we get started, keep on getting those requests. So if it was a one-time effort, most of the things that other software engineering processes and DevOps does would be fine. There are bugs, but they're small tasks. You can fix it. This is you're saying that you're going back to square one and cleaning the model again with unit. So for that, we observed that our velocity is not good enough. Our competitors were out at 6 or 7 features when we started. In 2021, we had 2 features. In 2022, we were only able to increase it by 2 more. Because the work from the previous process was still giving us a lot of problem. So this is the time when we started investing and investigating both in MLOps. So we're not just saying that there is a DevOps that we need to develop and operate and deploy, but there is another component to it where we are saying that you have data, you need to train it, and there is a loop that goes over how you run over. And when we started doing that, our velocity just exploded. I mean, we started going exponentially growth from 2 to 2 again. 4 different features in 2020. And these 8 are due by wave. Right? So in half the year we are doing 8. So what changed? What was the key that helped us scale this quickly? Is what no one will do. All right.
So continuing from here, I'll try to give a little primer on what MLOps is. A lot of people who are in the industry, we have a lot of, at least basic understanding of how ML works, right? So I'll give a little primer on what are the best practices, how industry define it, and then come to the main point of how we actually need it. So this is a typical development cycle of an ML system, right? The data scientist collects data, starts with one problem, collects data, cleans it, does some feature engineering, tries to understand how the problem will be solved. Then it's can't building the model, slowly increases the accuracy, does some iterations, evaluate, re-evaluate, and then come out with something that really works. Right? And then it is finally deployed on the server. So you have a service, and each can send an image, get the inference result back, or it can work similarly in different cases, type series data, LLMs, same principle. And that's what as Fahad was saying is software dev is done. A typical software development cycle is just complete now. We have bug fixes, we get into maintenance cycle, but it's not how software 2.0 works. So this is what unlike other call it software 2.0, that your program is not the instructions that we code. Program is the weights that our model does. So this is the programming paradigm, complete shift in programming. So it's not our intuition or our logic that we code using, let's say, PyCon. It's the way that the software does. That is the actual software. That's where the if-else is actually taking place. So what happens is the problem comes in with this model, this very, very simple model. 80% of the times when people start on this journey, they don't end up in an actually a real product. Reason? Because as Fahad said, and as it is well known, the concept like data tier, new features. And every time people have to go back to drawing board and start with it. So what they would do is, okay, we have new data, let's kick off a new notebook, start creating new models, and the cycle would go again and again. And this is very, very inefficient, not repeatable, not scalable, not maintainable, all those of nice software engineering things won't work. So we have evolved this thing called MLOps, right? So this is like DevOps with an ML touch to it. So the DevOps cycle was those two things, you develop and then operationalize and then come back and that was the cycle, but with ML, we have to like augment it with collecting data, training it, developing services over it, putting into operations, putting into field, collect more data and just iterate over it. And if we can automate it, it's very automated and for sure. Okay, and the whole MLOps cycle is built over it. So we have multiple components, we have data engineering, typically done, and then we have an annotation that comes into play. We get that data, we get some information out of it. We use that information to train our models, validate our models, automate those things, and okay, the pipelines can be built. CI/CD comes into play, then we keep on monitoring, logging, version control. And when we have like a number of models that are there, we need to build a good database on actually keeping track of how these models performed over time, how was I don't know what made them take, which cases failed, what things did not work, what worked, and we can have all of the dashboarding. So MLOps is all of this thing combined, giving us a nice whole picture and the whole process. Fair enough. And similarly, in order to understand what MLOps is, we have to look at the negative case and what is not MLOps. I mean, what is not good enough to qualify as MLOps. Data science alone is not, right? Similarly, well, a lot of people think that there is, if you just take a model, deploy it, put a DevOps cycle over it, without actually the whole training pipeline and all those, it's not that model MLOps, it's just secret DevOps. Just research enough. So the main point is that all of these things lack of monitoring maintenance. So they in isolation, none of them in isolation can qualify that. So we have to be very careful when we say that, okay, we are, because it's a fancy term, we all say that, okay, we have an MLOps pipeline, we have a system that automates everything, but we have to be very careful that what we are doing is actually making sense. So just, and be wary that ignoring some of them actually can lead to problem, inefficiency. So we'll have to actually completely embrace all of these things to in order to make systems operational, usable, scalable. Okay, but so this field is now a decade old in a way. We do not have very good maturity models that can actually encompass the complexity, right? But the one which is close enough is the one which is introduced by Google. It's a very simple model. The first one, as you all know, we have done that. We take notebooks, we analyze data, and that was the process that was explained in the first slide, right? So we have everything manual. Then we figure out some of the so we some patterns. So we said, okay, if we can automate this stuff, we can actually operationalize or automate some of these operations, at least the training part. Right? So first thing that comes into play, and when we start automating an ML pipeline, is the automation of the training pipeline, because that is a process which is very repeatable. You have tons of data, you have your training code, you have your model, and then you can actually put it into a loop and you can make nice data store that will just keep on fetching data, and the model training kicks off. And then the validation is done, you have a dashboard. So this is the first level of automation that some of the pipelines are automated. And then this is actually, so let me tell you, this is where we actually started thinking that this was not good. So without actually knowing the Google's model, we realized that, okay, we are good, but it's not working well for us. We need to actually invest more in automation. So naturally, related with what they are saying is that we have more automated pipelines. So model is trained automatically. So the data comes in, goes to annotation team fills out, figures out, okay, these cases are not working. We have an alarm raised, okay. These are the failure cases. We fetch that data, get those videos, get the frames out. Get them annotated again, and then the training automatically kicks off. And the training is completed, then it's whole testing and validation, which is where I'll describe that why is it so complicated. The testing and validation of models in a more complex system like ours, and that is taken off. Model is deployed, data is collected, and the whole cycle can be automated to a much larger scale. Not just a single loop, but the loops of loops can be automated as well. So this is what we see on Google's and Amazon's website, that this is what MLOps cycle looks like. So they have this SageMaker and everything, and they sell this. Okay, the problem is it doesn't work for us. It's not, this model doesn't describe the complexity that we are facing. And when we ask ChatGPT to describe our situation, this is what we came up. So Google's maturity model may reach a good shoe, but it doesn't fit every foot. Our system is a more complex dance that requires a unique therapist. Okay. So pretty much. So our dance is more complicated. So this is what we are going to talk about. The main thing. This is the academic version. This is the typical bookish version of what MLOps is. It should work. Google says it should work, and the model should encompass the whole complexity. So what have we done to achieve this thing? And as Fahad said, and let me actually reiterate some of those numbers here. We have bunch of features that are for which we are getting data back, right? These are these 15 models require 15 features require 10 different models to come into play. Okay, some of them are combined, some of them are in isolation. So it's a complex stack of competition. It's not just read. It doesn't go like, okay, take the data, run the model, get the output, and validate. So we have like a model running on the dynamic, a model running on the driver facing side, a model running on the road facing side, and multiple models running on the road facing side. Because in the beginning we figured out that having a lane detector as an independent model and a vehicle detector as an independent model actually works better, because lane detection and distance requires a lot of geometry, whereas the vehicle detection is very simple object detector with a region, right? So that geometry had to be taken, and a lot of camera parameters and fundamental computer vision geometry was required. So these are multiple models, multiple algorithms. It's a whole DAG, as I said, that actually keep on converging into giving us the final solution. So building, testing, and validation pipelines for that is one thing. And then we have like 45 different people training their model every day. Like every model takes 5 days to train on a individual, right? And we have like this wonderful team, like almost 10 models every week that they're working on. So each model, we have people analyzing the data, some people actually working on a code, somebody cleaning up the data. It's just a very complex pipeline. And above all, we were able to like hit close to 90% accuracy with all of this working in. So how did we actually achieve this result as far as this working on Shiekh? So this is like So this is what typically is a cycle. So we, as I said, identify problematic scenario, extract frames, get it annotated, the annotation is reviewed, and all those data is put into what data store. Then our flow pipelines take off for training. When the model is trained, we have a test bench, which is a big test infrastructure that we have. It's kicked off. We have then video data sets that take those videos with their telematic data, feed it into the main pipeline. These algorithms run on it on tens of thousands of videos to validate if a particular set of models and the associated algorithms actually work. And then we have all those dashboards. So this is the whole MLOps pipeline that we have. It's very typical one. But again, the devil is in the details. So there's a lot of rocket science. There is none. It's like so many obvious things, but they have to be put together, and they have to be like orchestrated in a very clear way. That okay, we were not doing something for sake of it. So we built a lot of systems actually from first principle. So we thought that this is a problem we are facing. Okay, add it first. So here's a solution added to our whole infrastructure, put it into and like the MLOps pipeline is called because everything goes down in circle. So what we do is we start with a data store. We have traceable training data, validation data, videos, images, standardized in a certain way, put together. We do like cleaning on it, ETL stuff, and then we need to like standardize our archival with videos and images and telematic in a way, standardize it. And I will dive deeper into it. This is again, as I said, no rocket science, something that everybody understands. Okay, this is a database that we have to keep it. What are the features, what are the main factors that actually led us to this? I'll dive deeper into it. But after the data store, as I said, we have a training infrastructure, building blocks, like multi-cloud shared solution, right? All of these great cloud providers, other companies have their solutions. SageMaker, AI Studio, Azure Studio, IBM Watson. So training infrastructure is not a biggie. There's tons of it. We built an in-house ground-up thing. We started with SageMaker, expensive. Moved on due to building our on-prem solution. Like some of it is on-prem, some of it is in the cloud, but still the whole solution is built in-house. And then our go-to stack for doing a lot of MLOps is Kubeflow. And another workshop tomorrow on Kubeflow by our team, Phenomenal Labs. So we'll be giving some hands-on overview of how we use that. And then after the training infrastructure, the bigger one, we go to something which might not seem too fancy again. So it's a database of all the nodes that we take, right? So but it's very important for model workers, right? How do you keep the genealogy? How's the training tracked? How's the code tracked, right? So all of those things, and how did each model fare? Okay, what did we do? What did we do? Teacher student, or did we do some other kind of fancy stuff to get that model trained? So we can compare across the methodology, also not just the technology, right? So again, anything has implementation, very simple Kubeflow based pipelines written to register models, to keep track of everything. And then the one fancy thing that we do is we integrate it with our deployment pipeline. So once you train a model and once you decide that to be registered, then it is automatically pushed to our reference pipelines where you can call the service, give it a and have and we have tooling that we can actually compare inference across models. So we can give it one image and see how it fares, or a set of images, how it fares across models. So this is very, very important. But again, okay, and the last thing is our testing infrastructure. This is where actually the whole idea, their whole fruit. The testing infrastructure is a system for automated testing on video and telematics. Remember, our problem is complex. Our problem is not just image training. It's not just video. It's actually a video along with a lot of telematic data, including, let's say, RPM of the car, the speed, maybe the GPS location. There are so many things that come in and actually play a role. So our testing infrastructure has to provide, has to provision for this. That okay, what kind of speed that we want to, what kind of data do you want to use to test this thing? For example, close falling at high speed, we need a data set to handle, to actually to detect that scenario. So our data store is different, and our test infra is again a very complex structure that I'll talk in a minute. That it should cater to all the concept drifts, long aliases, etc. So testing infrastructure has to provide that capability as well, and it has to be fast and cheap because we run these tests from tens of thousands of videos every time on this. And every time we come up with a new fancy way of smoothing. Okay, so data store is complex. So diving deeper into data store, we have videos coming from multiple sources. We have older generation cameras with lower FPS. We have newer generation cameras with higher FPS. Okay, then we have videos that we can recall from the edge. They are stored for longer purposes, so they're not stored at full FPS, so they may be 5 FPS. So multiple versions of videos are captured in different places. And also we should be able to import third-party data sets. So all of them should serve a final purpose of training and testing. Right? So we have to build tooling on how to resample, how to resample the telematic data, resample the video images, and so on. So similarly, telematic data can come from a variety of sources in our case. With each generation, our storage and our title and our pipeline actually changed. So if we want to create a data set from let's say all the rainy videos, in which they are the internet, so it may be from different hardware with different characteristics, and it has to be standardized. And similarly, as I said, there is a lot of geometry around it, so we need camera parameters to validation geometry. So that's also generated at runtime and so on. So and output is actually pretty complex. As well, we need to have all the huge Cartesian product of all these possibilities to get what the final data set is. So for example, it's hardware dependent. So if we have our hardware on the edge, which actually detects at 2 FPS, right? And we have video that is 30 FPS, then we should have a data set that should emulate everything at 2 FPS to make sure that what we're going to actually see on the edge resonates with what we can test on the cloud. So it's not possible that we actually generate an event at 2 FPS on the edge and we test that model on 30 FPS. Because yes, 30 FPS is happening, but a lot more information. You're very likely to detect, let's say, the sensitive usage of a 30 FPS video as compared to the 2 FPS processing that we do on the edge. So our whole data store has to keep that target in mind as well. So we need to keep those different versions. Okay. So the target is pretty complex as well. And then there's a modeling done too. So we have a video in which we detected something, and then later on we want video and which we detected, let's say, a vehicle in front of us, and our machine team said, okay, there are 5 vehicles in front. But later on we need to actually calculate stop sign violation, red light. And that data has to be reused. So on the same data, we need more annotations. Okay, or maybe the definitions change. So that evolution has to be put into play as well. As I said, multiple targets. And then the test infra, as I said, is pretty complex. 25 engineers at the same time say, okay, you want to run a test around. Okay. And you need to have a very scalable infrastructure that can allow all of them to test, like, say, 5,000 videos, the job runs for a day. How do you orchestrate all of it, right? So there's a scheduling problem, there's a costing problem that comes. So a test infra has to cater for all the demands that are in the way. And then, as far as that, every scenario comes with their own challenge. So we have to, put our testing into play for different scenarios also. So the complexity of building the system is multi-fold. So right now at our test infra usage, we have tested more than 260 models at this scale. We have 1/3 of a million video samples stored in our data stores, and we have run 215 million tests on sample level. That means we have a new noise filter, okay, right? We have a new, and see if we can detect close falling better. We have a new algorithm to detect those anomalies as far as shown. And we need dashboards. Actually, those are the main things, major part of the MLOps, right? How do we quickly zoom into problematic scenarios, the tail cases? So we need tooling to establish that. Okay, this is one major cause of failure. Okay, now we pointed it out, go back. So that's what we develop. And this is the result. With building all this infrastructure, our PS rate actually is going back. Our model training was taking up to the whole training cycle and analysis cycle was taking up to 2 to 3 weeks. 2 to 3 people are actually involved at different stages. Not all can be done with rate. So our model rollout, our model experimentation is on next level, and that has led to the explosion that we saw. That we started with 2 models, 2 features. In the first year, added 2 more, then added 4, then added 8. So it's like the exponential growth is because of the very simple first principles development of these fields. No fancy stuff, nothing off the shelf. Okay, just figure out, okay, this is one technology that you want to work with, and just to start iterating on adding those features, figuring out what is required. So, lessons learned. Well, every data store is not a data store. So if you want to save the data, you have to be very selective, you have to be smart. If we have 2 billion videos, images in a database somewhere, how to select those? Which ones to pick to create, right? So it should be smart. Take it seriously. And collaborate across teams. So the reusability comes into play. And again, data set should cater for changing scenarios, conceptive, so that accountability of each model. Okay, this is a model that failed on this thing. What is the new model? So that that follow-up has to be very clear. We should be scalable. You've looked at the scale that we have, so our data store, our tested cluster, everything should be able to take it to a lot of responsive way related to scalability. I mean, we don't want 10,000 videos test to be completed in 5 days, 3 days. We want it in a matter of hours so that we can iterate faster. And cost effectiveness is there. So what's next? We're adding generative AI capabilities in our data store. So if you have to detect lot of images, I mean, where do we get data from? We have 1 billion images, but who's going to actually aggregate all of them? Who's going to find things from there, right? So our in-picture thing that stable diffusion gives us, okay, we can make it person job, right, and add it to our data to train our models, right? So generative AI is playing a big role, and this is the first thing. I think I think this is the main thing that we work with yet, but there's millions of other things. With video coming in, we can actually simulate a lot of accident scenarios, right? So generative AI is a game changer for us. So our MLOps is going to the next level. So it's not just going to serve the AI, it is going to have its AI of its own. And very related to that is using models like Clip. So what I was saying is that we have 1 billion images of data store. How do you find images with people talking? So if we have these foundation models which will actually do text-based searching over images. I mean, what does it want? We don't want to actually go through annotation. So annotation workload is going way down. We are scaling up in terms of our clients and revenue with customers, but we are not scaling up our annotation team at all because we are using AI to do a lot of auto annotation. So our validation is done on the edge, our validation is done on the server side, and then read validation. I mean, we have heavy models to do another, and then in the common case, the safety validation. So we're doing I'm building on those layers as well, using better data. Okay, that's it.
So, yeah, there might be a cost to maybe that make it work. You all you were and it's of course fair as you elaborate if you use some magazine in the advantages is not your rating. I think the market is you see the way the artists out in the out the things although I'll give forward that word that will also introduce that.
Perfect. I'll take the question and I'll tell you the second question. So the question is that if you have a new sensor coming in, and that is the case, as always, with the next generation of camera that you're working in, has a separate camera for the license space reading. So exoneration and other there's so many cases there. Insurance, exoneration, things like that. We need LMDR, the license plate reading. So we have actually got a new sensor in our camera for the destination tracker. So now instead of having 2 cameras in a dash cam, we have 3. One for general front view, one for focus view, and one for the way we collect data, I think Fahad is actually leading one of those efforts.
So you got as Numan said, the data is the data. The problem is still born at the data store side, and that is a good thing about it. That when we are having to the data, that data uses data store uses archive. That it picks up those videos where we have it with data. Which not that we you this one with videos will running that I mean this to be a thing. So that's one thing. Just putting the data in the data stores rather having attributes and other annotations with that data helps us identify what to pick and what to work on. So all of our data stores are ignorance. This is I don't really have way. So the data store, the metadata source of picking and what is key in the data store in the data set and very use. So that this availability is one data you can get select the data variant and so on. The second important thing is that this is separated from all data. So when you select the data, you get a single source of the multiple sources of data are reduced to a single standard format so that a more thing is just to have data output as a thing and that's part of the subject. So over it, I would go to work. This was the user team at Stanford. Each Windows event to be and sign the larger meeting. So you must bring them last question.
So my question about the slide is over there and it's about browser. Actually, the mobile is the presenting as a drug. So the question is no need to products managers, but I also need the product managers that come up with a sequence with and I want to name the model of that. But the AI and the business running is going. So how actually what are you doing this thing?
Okay, so when we first launched our product, we didn't have an adversary, to be honest. So it was just a camera and a annotation key, and what we had was an ML algorithm which used to pick up breaking errors. So if you have an accelerometer, you can pick up breaking events to measurement that's only, and say that hey, there's a hard brain, send it to the server. And once we collected sufficient data, then we started training the model. So when a product manager and very helpful our product managers that can understand this type of thing. When this type of request comes in, then initially we come up with bunch of heuristics which are not collecting data. And that comes from smart.